You know, I am perfectly aware that I talk too fast. And anybody who's survived any of my courses knows that I talk too fast. And let me just tell you, if I'm going too fast, I just want to remind you, you've got keyboard shortcuts given at the bottom of this page here that will help you with like little rewinds on YouTube. I know it can be kind of difficult to move that little slider and very precisely go back just a few seconds to hear what I said again. I think the key is J or Control left. I'm not sure. Whatever it says on the bottom there, I always forget my YouTube keyboard shortcuts. But that can be a really useful way to just hop back 10 seconds, 20 seconds, 30 seconds, and hear something I said again. And again, I apologize. I know I talk too fast. I want to talk for a little bit about the fact that climate change isn't just an idea. Anthropogenic climate change isn't just an idea. There's in fact a whole lot of evidence, multiple lines of evidence for climate change. And in fact, that's one of the major strengths of modern climate science. One of the major strengths of our understanding of climate change is that so many sources of independent information seem to all be in agreement and fitting together. We don't hear from the people who study ice that the planet seems to be getting warmer, but from the oceanographers that the planet seems to be getting cooler, but from the atmospheric scientists that the planet is getting warmer. No, we have all these different sources of information that are all in pretty good agreement. That's a real strength. That's something the scientific process tends to look for to build confidence in results. Examples of the types of evidence in the are the observations, which come from systems that are peer-reviewed. They are made by different technologies in different countries, by different groups. That's all a really good thing. If the automated weather stations were not showing a temperature trend, but the manned weather stations at airports were, we'd wonder what was going on. The fact that different technologies used in different parts of the world for different purposes all show the same message is very strong evidence that this is working, that the scientific process is working, and that we are correctly identifying climate change. Just to give some examples here, ice cores, when they drill down and extract those cylinders of ice out of an ice sheet or a glacier or something like that, can reveal information about changes in the composition of the atmosphere. We'll learn more about how that's all done later. They can tell us more about the temperature of the atmosphere and so on. There are all these different networks of instrumentation on land or on sea, run for different purposes, from aviation safety to climate monitoring to agricultural purposes to safety operations for ships at sea. All these different networks use different technologies, different instruments, and they have different procedures, and they all showing basically the same thing. That's good news. That is a strong endorsement of that we're doing this right. Same with like the addition of satellite observations. You, of course, are familiar with the use of satellite imagery for things like, looking at weather patterns in clouds or monitoring something on the surface of the Earth, like land use. But there's actually a lot of things you can do from satellites, like monitoring ice cover or snow cover, monitoring temperatures and winds and so on, moisture in the atmosphere. There's a lot of fancy techniques that we'll be learning about over the course of the semester that you can extract meteorological and climate information from satellite data. There's also this whole business of all these different kinds of theoretical work that are providing multiple lines of evidence about what's going on in climate and climate change. Theoretical work, development of new theories, new models, new ideas, is also all peer-reviewed. You can't just go out and write a model and start publishing work about that with that model. Every detail of it is going to be combed over by experts to see if you're doing it right. Same with some new theories, some new equations or something like that. It's all peer-reviewed, and it's going to be made by lots of different researchers in lots of different parts of the world with different agendas for different purposes. And that's an amazing thing, because all that theoretical work is also telling us the same thing about what is happening in climate. This could be conceptual models, like that diagram we had with all the arrows showing shortwave and long-wave radiation up and down through the climate system, or it could be numerical models, these big model computer programs that run on supercomputers to simulate the climate system. All of that stuff is thoroughly reviewed before any of that work gets published or gets accepted by science. There's all kinds of specialized statistical tools that are developed for use in climate science that the jargon is their tools designed for detection and attribution. How do you know that these temperature changes were being caused by these gas changes and the concentrations in the atmosphere? Those are specialized tools that were developed for climate science. There's also this whole business of like paleoclimate reconstructions. How do we know what climate was doing in the past? That's geology, that's ice science and so on. All of that is independent. The geology people didn't read the theoretical meteorology papers, and yet they're all coming to the same conclusion. That is a very, very strong bit of evidence that we're doing the right thing. And we can see that all around us with various things that are changing that we can observe in our world. The jargon for this, again, is that these are climate change indicators. Things that are going on in the climate system that seem to be indications about what's happening in regard to climate and climate change. In fact, this diagram, which I just extracted from the IPCC report, gives us a list of a lot of these things, all of which we're going to be talking about in a great deal more detail in further lectures in this module. There's going to be changes in the atmosphere, changes in the ocean, changes on land, and changes in the cryosphere, or in the ice system. If I just zoom in real quick on the atmosphere, we're going to be seeing all kinds of climate change evidence in the Earth's atmosphere. Your book picks apart the fact that there are different temperature changes happening at different heights in the atmosphere. Down near the surface, we generally are seeing that the temperature is rising, but we see, let's see here, and in fact through most of the depth of the troposphere, but then they actually show that there's actually cooling happening up higher in the atmosphere, in the stratosphere. You may not remember the stratosphere, it's the next layer up in the atmosphere. It extends from about, 11 kilometers to 50 kilometers, something like that. And actually, we have stratospheric cooling going on. Now, we're going to pick this all apart in a great deal more detail later, but these points are related, as the changing concentrations are resulting in a different temperature distribution in the atmosphere. But of course, features of the Earth's climate system, like the cryosphere, is down at the surface. Temperature changes at the surface are what's causing their changes. We think mostly of climate change as being about temperature, but the changing temperature results in other factors too, like increases in the humidity in the atmosphere near the surface. A warmer world is a more humid world. This is due to an equation that you learned about without ever actually seeing back when you took ATSEVS533. It's called the Clausius-Clapeyron equation. This was the equation that had the graph where as temperatures increased, the amount of water vapor the air could hold increased. Okay, we're going to pick that apart in much more detail later, but for now, at least you know, hey, as the Earth gets warmer, the air can hold more water vapor too. And we're going to see that that's also going to be related to long-term changes in the large-scale atmospheric circulation. This is going to be things like shifts in where the jet streams are happening, shifts in the storm track, where are we expecting the features of the general circulation, like, to use terms from your ATS-113 class, things like the Hadley circulation or the subtropical highs or so on. These are all features that you learned about it back in like ATS-113. It's not actually due to the greenhouse gases itself, it's due to the temperature changes associated with the greenhouse gases. By the way, I think this is our first time of seeing that abbreviation, GHG. GHG, greenhouse gases, okay? So, but that's a real thing. We're going to have to be worried about, are we shifting the positions of the jets? Are we changing where cyclogenesis happens and our storm tracks and so on? That all has very large potential impacts. When we observe the atmosphere in the context of climate change, of course we immediately come across the cause of all this anthropogenic climate change, namely the increasing concentration of carbon dioxide and other greenhouse gases due to human activities, which we'll be talking about quite a bit, especially in the next lecture. The changes in those gases and the changes in the temperature, the distribution in the atmosphere will also result in changes in cloud cover, changes in the amount of water vapor in the atmosphere, changes in the amount of aerosols that are in the atmosphere, changes in the amount of ozone that's in the atmosphere. All these terms will come across in more detail as we examine these climate change indicators. Now, everything I showed you so far was atmospheric changes, but we could talk also about the impacts in the ocean. As the planet is warming, what we're finding out is the surface of the ocean is warming as well. And in fact, through some layer near the surface, through some depth of the ocean is warming as well. And of course, what many people know about the ocean and climate change is about the increase in sea level. We're going to talk about exactly how that all happens and how much to expect and so on in a future lecture. But we know, because we're environmental science people, that climate change, one of the expectations we have of climate change is that we're expecting sea levels to rise. And in fact, we are observing that sea levels are rising. There's also going to be changes in the distribution of salinity in the Earth's ocean. That's a complicated story that we'll tell more about when we get to the oceanography part of the course. But changes in the rate of evaporation of fresh water out of the ocean, which leaves the salt behind and increases the salinity. We'll be working on creating different patterns of salinity in the Earth's oceans, and salinity is a factor that determines like the density of ocean water and drives certain currents and so on. And most alarmingly, if you're a living thing in the ocean, is we're going to have ocean acidification. By the uptake of carbon dioxide from the atmosphere, the ocean stores that carbon in the form of a weak solution of carbonic acid in the ocean, leading to acidification of the ocean, which creatures who live in the ocean and breed in the ocean and eat things that come from the ocean don't like. Okay? That's all a big problem. We don't live in the ocean. We don't care about the ocean. We're always dumping some crap in the ocean. Yeah, but what about land? We live on that land. And there's going to be all kinds of changes in the frequency of extreme weather events. We're going to actually talk about that in the next lecture. We're going to see that there are going to be changes, obvious changes in the distribution and the quantity and the extent of snow cover and ice cover and permafrost and tundra, all of which is strong evidence that the planet is warming, and worse yet, sets off certain feedbacks. We're going to learn about like the ice albedo feedback that is going to happen when places that are normally covered with ice are no longer anymore. We're going to learn about the feedbacks that happen as permafrost thaws and decaying vegetation in the previously frozen soil now can release carbon dioxide back into the atmosphere. These are all important changes happening in the soil or at the surface of the Earth. There can be big changes in the distribution of precipitation on the surface of the Earth, changing patterns of runoff and soil moisture and so on. We can have, from a more social point of view, we can have changes in the amount of precipitation leading to flooding and so on. But it has agricultural and social and safety impacts. And of course then there's the whole scary story of all the changes in the cryosphere. Changes in glaciers, shrinking aerial extent of Arctic sea ice, glacier retreat, changes in the ice sheets of Greenland and Antarctica that you could actually measure from space in terms of like the actual gravity of the ice sheets themselves. When we get to the cryosphere stuff, you're just going to be amazed by all the horrible things going on in the cryosphere. Now, before we go on to our fifth part of this lecture real quick, let's actually answer two more quick questions. One of the strongest pieces of evidence of global warming is that A, overall the amount of water vapor in the atmosphere is decreasing. B, all locations on Earth seem to be warming at the same rate. B, multiple lines of evidence are in agreement. Or D, multiple lines of evidence disagree about global warming. Which of this is the strongest piece of evidence of global warming and climate change? Make a choice from those four options and get a little feedback before you move on to question 8.